Just play dice with the universe.
إغلاق السوق الكويتي من الأحد إلى الخميس 12:30 على شاشة العربية.
From the very beginning of human history, new ideas have been inspired by the potent combination of curiosity and observation. In today's technological world, everything you touch, use, see, or do, from striking a match to sailing, railing, emailing, flying, fighting, drying, tying, threading, sledding, trucking, chucking, plucking, timing, climbing, rhyming, typing, swiping, piping, wiping, tracking, cracking, jacking, texting, requesting, talking, walking, chalking, or watching this show is possible because someone, somewhere, observed, experimented, and transformed what was once just an idea into a useful and powerful tool. As incredible as these innovations and inventions are, they may soon pale next to what these explorers, past and present, have discovered and are uncovering. By peering into and probing the depths of the most powerful, tiny, and weird universe imaginable. The quantum universe, a paradoxical realm of seemingly unlimited potential, where fascinating phenomena are being harnessed and developed into new technologies that may alter the world as you know it. Journey into this weird and progressively wired world with the Quantum Tamers.
Before John Bell and later Alain Aspect came along, all we could ever really do was just argue about the weirdness of quantum mechanics. The Schrödinger equation tells us that a cat can be both alive and dead, and nobody knows what that means. It's just weird. And these arguments went on for decades. What John Bell did was put some mathematics and some quantities around the quantum weirdness, and what Alain Aspect did was come along and verify those measurements in the laboratory. So in essence, between John Bell and Alain Aspect, we were able to measure the weirdness of quantum mechanics.
Alain Aspect's experiments established that these quantum effects were real, even if it wasn't clear how to make sense of them, using our normal way of thinking. What's more remarkable is that these experiments inspired a generation of scientists to ask, how can these weird quantum features be useful?
Quantum mechanics gives us a phenomenally accurate description of the behavior of light and matter. This understanding helped 20th century scientists and engineers develop all sorts of technologies, including, for example, the laser and the transistor, which are at the core of our electronic world. These relatively large-scale quantum devices function without, in any overt way, exhibiting the weird aspects of quantum mechanics that we've been talking about.
These familiar technologies are all products of the first quantum revolution. But now a second quantum revolution has arrived, based on two major developments. First is the technological ability to directly control the weirdness of the quantum world, including superposition and entanglement. And the second is the rise of the information age. So ready or not, here comes quantum information, or QI if you're texting.
Well, what got me thinking about quantum information was in 1985 I came across a paper by the American physicist Richard Feynman in which he talked about the possibility of computers operating on quantum principles. And this came like a bolt from the blue for me, because up until that point I was more accustomed to thinking of information in very abstract terms. In the ordinary everyday world, it's difficult for us to separate the idea of information from content and meaning. But we can get an idea of why information is physical if we think about, for example, what we would do if we were asked to point to information. And we would always point to a piece of paper with marks upon it. We might point to an optical fiber. We might point to a hard disk. In the case of a hard disk, we can see that information really does have some physical content. For example, when you want to store some information on a hard disk, you have to pay real money. You have to go out and buy, say, a 100 gigabyte disk. It doesn't matter what the information actually is, but the fact that there's a certain physical quantity there that you pay real money for tells you that in reality information is physical. For example, I'm talking to you now. Information is being conveyed using sound. I could write a letter, and the information would be stored as ink and marks on paper. Once you get the idea that information is physical, you then begin to wonder whether the laws of physics either constrain how information can be processed, or, in the case of quantum physics, gives you a completely new mechanism for processing and communicating information.
This is information. The proper use of it can bring a new dignity to mankind.
Now you're wondering, classical information, quantum information, there's a difference? There is, and it all starts with the humble bit.
A bit is a fundamental unit of information, of classical information. It is encapsulated into physical system which can have two states, either something which is on or off, something which is charged or discharged, or something which is here or there, or, in mathematical terms, a 0 or a 1. In the quantum world, we have quantum bits, or for short, qubits. And these qubits can be in superposition of being in 0 and 1 at the same time.
And it's the ability to manipulate the world at that level of quantum weirdness, of quantum superpositions, that enables us to do computational tasks in quantum mechanics that are impossible, or at least very difficult, using conventional computers.
Our technologies are already approaching the boundaries of quantum information, and our transistors are approaching the size of a quantum bit or a qubit. And we have called this Moore's Law in honor of the founder of Intel, who predicted it 20 years ago. And in fact, over the course of the next 20 years, we expect the transistors, which are the heart of our computing devices, to approach the size of a single atom.
So the second quantum revolution really consists in us today being able to manipulate individual quantum systems, individual molecules, individual atoms, or in my case, individual photons. Whereas so far, after the first quantum revolution, we were able to manipulate ensembles. For instance, a laser would produce billions of photons, not individual photons, but billions. And today, the fact that we can really manipulate, master individual quanta, as we call them, opens a huge new area for technological developments.
One of the first accomplishments of this second quantum revolution is the ability for physicists to build incredibly precise tools, like an atomic clock, the world's most accurate timing device.
These days, the precision of atomic clocks is such that we're able to if we made a clock and if we could keep it running for about 60 million years, it wouldn't lose more than 1 second. It turns out the added bonus of the precision and quantum control we're able to achieve with the atoms we use for atomic clocks also is the basis for good qubits.
So if you can control individual qubits, you have an amazing clock. But if you can scale up and control the interactions of dozens or hundreds of qubits all at the same time, you don't just have a bigger quantum clock. You create a quantum computer, which has the potential to be the most important invention of our time.
Quantum computation can be considered a revolution in the theory of computer science. What we think today is that quantum computers will be able to perform certain tasks exponentially faster than classical computers. And why is that? So there is this very important fundamental thesis in computer science called the modern Church-Turing thesis. And what it says is that all regular classical computers are essentially equivalent. It's not that they exactly perform with the same speed, but they act according to the same rules, they behave similarly, and if you tried to perform some task with, say, your laptop, and then you try to do the same thing with another computer, it will sort of behave approximately in the same way. Quantum computation, it just is completely out there, out of this equivalent class.
Quantum computers are based on the fact that the quantum state of a computer memory contains much more information than its classical description.
A quantum computer will also be different in that it will manipulate and store quantum bits instead of classical bits. Classical bits can be in two states, 0, 1. Quantum bits can be in many possible states. And this new range of possibilities lead to new phenomena such as entanglement and interference. And we believe that this is what can give a quantum computer its power, these new phenomena.
Just how much more powerful? And to what end?
Well, one of the first applications of a quantum computer, and one of the most useful, is to simulate quantum systems. This is not something that most people are probably going to want to do at home, but it still has huge potential applications.
So to understand quantum simulation, it's important to think why we just need simulation at all. So consider an aircraft simulator. Why do we have an aircraft simulator? Okay, an aircraft simulator is a box. You go in, it's got a wheel, it's got a joystick, it's got instruments, and you go in there in the box, it goes back and forth, you move up and down, you take your simulated 747 in for a landing, like that. Why do we have that? Well, we don't want people taking real 747s in for a landing until they know what the heck they're doing, okay? So quantum simulation is the same thing. You have some big, complicated molecule. It's like a 747 of molecules, right? This gigantic thing, it's exhibiting all sorts of weird quantum behavior. You want to know what to do with it, but you don't know how to control it. You don't know how to make it do what you'd like it to do. So what you do is you simulate it on a quantum computer.
For instance, a quantum computer might help design new superconductors to run magnetic levitation trains, or new drugs to treat diseases. And a quantum computer could help simulate the atoms in the drug to tell us both how to make the drugs and how we'll interact with other chemicals. For physicists and chemists and biologists, all these things are really important. The chemistry of atoms, the behavior of materials all depend on quantum mechanics, and a quantum computer is really good at simulating that.
Others foresee a different role for quantum technologies.
Quantum mechanics is now giving us the tools to sense things better than we've ever sensed them before. We can sense mercury in fish. We can sense lead in toys. We could perhaps sense bombs along the side of the road. Using quantum mechanics, we can make the sensors more robust, more precise, more sensitive, and we can compact the sensor. We'll be able to use these sensors broadly in an environmental setting.
But what caused an explosion of interest in quantum computing was Peter Shor's discovery.
Well, what I did was I showed that if you could build a quantum computer, which is a hypothetical computer that no one has managed to build yet, you could use it to factor large numbers. So if you take two numbers, say 3 and 5, and multiply them together, you'll get the number 15. Now, factoring is the reverse of that process. You start with the number 15, and you want to take it apart and say that it's 3 times 5.